Namaskaram. Today we'll go ahead with our earlier idea of Hamiltonian matrix, and we'll prove that the Hamiltonian matrix is a Hermitian matrix. Hamiltonian matrix is a Hermitian matrix. So first of all, what is a Hermitian matrix? A Hermitian matrix is given algebraically by like this. Say the matrix is A and it is represented likewise, then Aij equals to Aj star, or the complex conjugate of Aj is Aij. So this is the idea of the Hermitian matrix. Now I will start with the Hamiltonian matrix and on the equation that the matrix mechanics equation that we have used before. Here see, it will be in this form: IH cat, isn't it? dci dt gives you summation j h I j c j, isn't it? Okay, now this is measured at a constant time t, this thing also. Okay, now from this we have to derive something which we know that if a particle is in a state, so this or this or this or this, then it can be represented in the form like this. Say this with the basis vector, one of the basis, this is another basis, and so and so. Okay, now what we'll do, we'll see what is the probability of finding the state, finding this state. Probability that the state is this will be this thing square, or C1 times C1 star, isn't it? Similarly, P2 will be C2 square, C2 times C2 star, isn't it? But what we notice is that this probability finding in this state plus probability of finding in that state gives you and this thing must be equals to 1. Why? See, the probability of finding in this state and the probability of finding the particle in this state will give the total probability of finding this particle in either this state or this state. The particle, when detected, can never be in any other state, so it will be either in this state or in this state. Okay, so these two things form the total universal set of the system. It is either in this state or in this state. Okay, so this is a shadow Venn diagram. Okay, so the total probability is 1. Similarly, as we know the state is in this state, then the probability that we will find it in this state is 1. So these things, say we have this thing probability of finding this state is 1. We know that it is in this state. Probability of finding the state is 1. These things we know. Okay, so we'll make use of the ideas. We'll make use of these ideas and see how we'll make use. We know then summation ck square. We have taken k intentionally in order that we are not confused with the notations. This thing might be equal to 1, isn't it? So d summation k ck square is ddt of this is equals to 0. This thing will not change with time. Okay, so we can extend this thing dx square dt 2x dx, isn't it? 2x dx. Summation k, we can take this over here is equals to 0. Now 2, we'll move it over here. Okay, and summation k ck tk, this thing we have done, but we have this thing over here also. So how we'll manipulate this? We'll use this idea that ck magnitude into dck dt. Okay, now one thing we'll specialize here is that we'll not use a complex notation here. We'll assume that ck is real, so we can take these things out. Why we have assumed this? For we have the formula for this here, and here we don't have the amplitudes of the corresponding complex numbers. So summation k ck dck dt, we will not use this thing, these coefficients. This will just lengthen the calculation. dck dt will be written as summation j h, say I is replaced by k here, then k we can write here k j into cj, isn't it? Cj, this becomes equals to 0, or summation kj hkj ckcj equals 0. Okay, so we are fine. We are probably in the king's seat here, or say this thing equals 0. Now we have taken these things to be real. These things are real, and so this thing over here can be symmetrically written as by bisecting the number of terms. That means dividing by 2 the number of terms. This thing come here as hkj plus hjk ckcj. We'll give a glimpse of the idea here. See, hkj, if we let k to be 1 and j to be 2, then c1 and c2 plus h, k was 1 and j was 2. Now if we write in this form 2 1, this thing will come c2 c1, then c1 c2 is the common term, and we have h12 plus h21. Okay, so we have for every I and every j we have such a pair of terms, so we can write in this form. Okay, so from this 10 point we're going to solve something. Say ck and cj can take any real number, any real number expression it can take, if not any, at least arbitrarily many, infinite such expression. For such infinite expressions to be zero, these things see 0 is a real number, and this thing, these two are real number, then this thing must be real number. Okay, you can say that for this thing to be 0, then each of this thing will be equal to 0. You can say this, but this thing is the solution of the equation, but this is not actually the case. As the Hamiltonian matrix has been constructed, it has not been seen that every such terms when added together gives 0. For there are other implications that ck and ckj manifest each other in such a way that this thing need not be 0, but the total thing comes out to be 0. Okay, so at least we can say that this thing is real. For these things to be real, then hkj, say we denote it by is equals to a kj plus I b kj. Okay, and hjk we denote by a dash jk plus I b dash jk. Okay, now for these things to be real, this plus this to be real, this thing must be cancelled, this thing, so bkj must be equal to minus b dash jk. So we have one thing over here. So hkj equals akj plus ib say kj. If you take this to be b, and hjk is equals to a dash jk minus I b jk, minus I b jk. These things are equal, and these two things are practically equal with what we have seen over here. Kj and jk are equal. Okay, now if we replace k by j, then hjj will be equals to ajj plus I b jj. Okay, hjj from this thing equals a dash jj minus I b jj. So these will cancel each other, but ajj must be equals to ajj, then ajj must be equals to a dash jj. But this thing is a generalized thing, then these two things must be equal. A kj equals to a dash jk, for this is the thing from where these two things have evolved. So we can write now in a fresh manner h kj equals to a kj plus I b kj and HJK equals to AJK minus IBJK. See, we'll not see the coefficients in determining the magnitude of the numbers. Here B and B are equal, A and A are equal. So if something is written in this form, that Z equals to A plus IB and another Z is equals to A minus IB, though then these two are complex conjugates of each other, isn't it? Then HKJ, which we have written, is equals to the complex conjugate of HJK, or HKJ star is equals to HJK, or HJK star equals to HKJ. This gives us the Hermitian Hamiltonian matrix. Okay. In the next video, we'll try to focus on some physical examples. Okay, that this thing is Hermitian is of prime importance in later chapters, as we'll hover over. Thank you.